All right, so we're kind of moving out of the physicochemical properties section where we talked about like C log P and TPSA and stuff, Lipinski rules, Weber rules, and moving into computer tools that help us not only determine those parameters, but also like determine drug likeness and other things that we'll get to. And so the first thing we have to do is talk about how do we represent chemical structure through computer tools. How would you do it? How would you represent chemical structure? Maybe you've never thought about that. Like, what's a chemical structure? It's a bunch of atoms that are bound, and you have single bonds, double bonds, and triple bonds, and maybe stereochemistry. How do you represent that in a way that can be easily transmitted or maybe imported into a tool? I mean, that sounds it's a kind of a complicated computational problem, right? How like I can imagine drawing a chemical structure in a program, like drawing a benzene and drawing aspirin and drawing complicated molecule like Taxol or vancomycin or something like that. I could do that, but wouldn't it be cool if we could encode the chemical structure of a molecule into like just a series of letters? Does that seem possible even? I mean, think of all the chemical structures you've seen, and like, would it be possible to just encode the structure? And the answer is yes, we can. And it's a kind of just a systematic, almost like a computer language or something that encodes chemical structures, and it's called Smiles. Okay, so this has been kind of started around the mid '80s or so. Now even chemical drawing was not around forever. That was also kind of created in the 80s or so. As we got better better as chemists, better as organic chemists, and also just as computers got better. Because I was in high school in the 80s, and we didn't have the internet, right? That was like, it was pre-internet times, and so it was kind of a different world in terms of just doing science, and also how the literature was organized, and how you do computational searches, and everything like that was quite a bit different without stuff like the internet. The internet's really made everything better. Okay, so what is Smiles? So Smiles will be a kind of a text-based encoding of a chemical structure. That's it in a nutshell. Okay, so the acronym stands for Simplified Molecular Input Line Entry System, and of course, the funny thing is we're also going to see something called SMERCS, which is different, and there's another one too, Smiles, SMERCS, and I think there's another kind of funny thing like this that actually you can represent like chemical reactions and things like that. But Smiles is specifically for chemical structures. It was sort of started in the 80s. It's gotten a little better through the 2000s. Now you can almost represent any chemical structure this way, including very complicated structures with a lot of stereochemistry and things like that. Here's an example: ciprofloxacin, the antibiotic drug. It's got a pretty simple chemical structure. You got a couple rings, this piperazine and benzene, and another 6-member ring with nitrogen. I mean, how would you encode this as a series of letters, and as a text string that I could maybe like cut and paste and email to you? How would you do that? Well, it's all automated, which is great. It's usually people don't actually create these themselves. Computer programs are really good at converting these to Smiles. So the way a computer program might do that is it'll basically break each of the rings. So we have a couple rings here, and it breaks them, and in various kind of strategic points. And when you break all the rings, it actually just turns out to be a series of letters almost, which is pretty cool. And then the Smiles will just kind of define where those rings are again, if that makes any sense. But you can kind of see, we have 1, 2, 3, and 4. And when you break those all up, then it's just kind of a big, long, linear molecule that kind of looks like this. There's no more rings, right? It's just like a big, long molecule, and then it'll just encode where those ring attachments are. So now the molecule looks simpler, right, than when we had originally. And then this turns basically into just a bunch of letters that you can see the colorimetric encoding of where those different pieces are. But and you can see also like N is probably nitrogen, CC, and double bond is an equal sign, etc. This text basically, this sort of simplified structure got encoded into this series of letters and numbers. And you can also see what do you think like 1 and 2 and like the 3 and the 4 mean? Well, those represent the different, like wherever the bonds were broken, those are numbered now, and that's all encoded in here. So given this text, basically this will directly and unambiguously map back to the structure, which is pretty cool. The Wikipedia page on Smiles is pretty good and comprehensive if you want to learn a little bit more about it. Just, historically, I think it's actually kind of an interesting thing in chemistry. It's really revolutionized chemical informatics. This website on daylight.com is good. This company has done a lot in terms of chemical informatics and defining the language. There's actually like a language that Smiles encodes, and this company's been involved in all of that. It can also be looked up for known compounds. So if we look in PubChem, and if I look up morphine or something, you search down and you'll actually see the Smiles, and we'll do that in a second also for practice. We can also use chemical drawing programs like ChemDraw. I can just draw a molecule and it'll give me Smiles. Sadly, ChemDraw is super expensive now, so it's kind of it's the industry standard for chemical drawing, but it's so expensive that it's very hard to get it. And it's also one of these silly programs that has a subscription, so you buy like $1,000 a year for a subscription for forever. Yeah, that is very expensive, right? But there's other like tools that provide Smiles also. Okay, good. Here's some more examples. This is a very simple one, just to show you, like, if I have a very simple molecule like methyl isocyanate, which is just CH3 and double bond C double bond O, the Smiles of it actually is very simple. It's CN double bond C double bond O, which kind of just directly maps to the structure. So this Smiles and this structure totally makes sense. Vanillin is actually just kind of a fun one to look at. It's a pretty simple molecule. This is the most of, when you say synthetic vanilla, or like the vanilla powder at a coffee shop, that's what this is. It has the taste of vanilla, and it's actually this is what is present in vanilla bean also. Synthetically, it's like a gazillion times cheaper than extracting it from vanilla bean, but it's all the same chemical. And aromatic aldehydes, so almost all the aromatic aldehydes you can imagine, like with like methoxy group over here, different things on aromatic aldehydes all taste or smell kind of like sweet, like fruits and stuff. But vanillin has a very nice smell and a nice taste. And anyway, the Smiles of it, let's just see if we can kind of figure this out a bit. It kind of looks like that. C double bond O, what's that? That's probably the aldehyde, right? That's the aldehyde. And then it's C double bond O is connected to a carbon that looks like maybe they're calling it carbon 1, right? So there's carbon 1. And then it looks like there's 3 carbons, carbon, 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 and then an oxygen. So it's not even showing all the hydrogens and everything. I think the lowercase c's are considered aromatic carbons. So we're not even showing the hydrogens. But that still, this totally maps to this structure. All right, so that's C1. Then we have carbon, carbon, carbon. Those are like carbon, carbon, carbon. Then we have that oxygen, which is O. Then we have another carbon, and then OC, which is the CH3, O and the CH3, and then C1. So this the way that it encodes that there's a ring is we have C1 and C1, and those will be considered a connection or a ring, right? So the C1, that's C1 and that's C1, and that is how it encodes the ring, right? That's pretty cool and easy to see. Okay, so there's also something called Isomeric Smiles, which encodes the chiral configuration. It's kind of like, do you know RNS? Remember that from organic chemistry? So you can figure out the designation, the chiral designation of chiral centers using RNS, using the Koning-Gold-Prelog rules. Well, Smiles has a version of that. I don't know if it's exactly the same as Koning-Gold-Prelog, but it can encode chirality, the specific three-dimensional stereochemistry of chiral centers. So an example is nicotine, very simple molecule. And let's see. All right, so let's see if we can look at any of this. What do you think the lowercase c's are? The lowercase c's we determined from up here are probably the aromatic. Okay, well, maybe that's the aromatic ring, or the lowercase ones. And so if we just look at kind of the right side of this, that's probably all of the aromatic ring. C2, so there's C2 is probably going to be, looks like there's C2, carbon, 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 nitrogen, carbon, and C2. That's probably, it's definitely the benzene. And I see CCC, that's probably like that carbon, carbon, carbon. Carbon, 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 carbon. There's the nitrogen, and then there's C2, and then the other C2 is probably right there, and then of course that's connected to this. This other part's probably the other ring with the 5-member ring with a nitrogen on it. And I can't interpret all of this little stuff, but the N1 and this one I think refers to the ring, but what's the how's the chirality expressed? It's probably this little bracketed thing, and that is kind of the equivalent of like R or S, and you know, it uses their own little internal language, but anyway. Bottom line is chirality and the specific stereochemistry can be encoded, and it's through something called Isomeric Smiles. All right. Now this up here is not called. This is not Isomeric Smiles. This is called canonical smiles. So we have kind of two smiles: is canonical, which is just does not represent stereochemistry. Of course, these molecules don't have any stereochemistry. But then like a molecule like nicotine, it can be expressed either using Isomeric Smiles with the stereochemistry, or also in essentially the top format, and then it just ignores the chiral center and it doesn't define it. All right. So whenever you have Isomeric Smiles, that's usually the one you like to use because it actually encodes the stereochemistry. When we use PubChem as an example, we'll see that it actually has both. It has isomeric, and then it also has this stuff called canonical smiles. And usually, if we're going to copy and paste it, we're just going to get the isomeric one. All right. Okay, so we'll do a little demo here. We'll look these up. And this is something you'll be doing in your homework just to practice this and practice the use of smiles. So I'm going to go to this website, PubChem, NCBI, and National Library of Medicine. It's a government NIH resource that we can look up chemical structures and basic pharmacology questions and things like that. And we're going to look up the smiles for these molecules. We're going to prefer isomeric if it's around, otherwise we're going to default to canonical. Alright? This is the isomeric encodes the chirality. Okay, so desipramine, fluoxetine, darunavir, daptomycin. And let's see if we can get these. Desipramine was a tricyclic antidepressant, and it's achiral. Oops. 1 second. PubChem. Okay, our first one was desipramine. Alright, there it is. There's a tricyclic antidepressant. It's one of the ones we talked about. Whoa. It's one of the ones we talked about when we did synthesis of tricyclic antidepressants. And this one has a NaH on it. I think some of the other ones have 2 methyls on them. Okay, so if you just go down, there it is. There's the canonical smiles. There's no chirality, so this would be the one we would get. All right. Fluoxetine, of course, is Prozac, and that has a chiral center. Oops. Fluoxetine. I think this might have a. Oh, actually, I think I remember it's usually a racemic drug, so it has a chiral center, but there's not it's usually we don't care about that chiral center because it's racemic. There's canonical, so that maps to it. Darunavir, I think it's an HIV protease inhibitor, and I think it actually has some real important chirality. Darunavir, so we may see isomeric for that one. Uh-oh. Darunavir, there it is. It says an HIV protease inhibitor. Yeah, it has several important chiral centers. So I think this will have an Isomeric Smiles on it also. There it is. So this encodes all of the chirality, multiple chiral centers, whereas the canonical does not. Okay. Obviously, in terms of the amount of text, isomeric is a little bit more, but it actually encodes more information. Daptomycin. Daptomycin's an antibiotic. Where is it? Search. Okay. This is a crazy molecule. I don't think that's the real structure. I mean, it's not obviously a cyclic molecule like this. The three-dimensional structure will look a little different than this, but it's a peptide. That's a pretty big, crazy molecule, and yeah, its three-dimensional shape is not going to look like this at all. But anyway, it's a pretty sophisticated molecule with a big ring of peptide, and then we have some other stuff and like this alkyl chain. This will definitely have an Isomeric Smiles also. It's a fairly involved Smiles. It's nice because it encodes every aspect of the structure, right? And then the canonical won't encode the stereochemistry. Okay. How to draw a molecule and determine the smiles. How can we do that? There's tools for that. I mean, ChemDraw is an amazing tool, but that one costs a lot of money, so we're not going to use that. But this website on the National Cancer Institute website, Cactus, this has a tool that creates smiles, so we can draw molecules and create smiles. Let's give it a shot. We'll try to do this is one of our non-nucleotide reverse transcriptase inhibitors of HIV that we did. Let's see if we can draw this molecule. So let's see. Okay. So let's paste it in there. This is the cactus website thing. All right, how does this work? So we go to Start Structure Editor, and that'll allow us to kind of draw the molecule. Okay, there's the editor. I'll minimize this one. Let's see if I can draw that. All right, so I'll start with the benzene on the left, and then how big is that ring? It looks like it's 1, 2, 3, 4, 5, 6, a 7-member ring, right? I can give a 7-member ring tool, so I'll just do 7, and then we'll do our oxygen up there, and our nitrogen down there, and a 5-member ring there. Double bond, let's try the double bond utility. Double bond. Ketone. Oxygen. Let's draw ethyl, benzene. So it kind of fit the benzene up there without connecting it to the ethyl group. Okay, so then we can submit the molecule. Was it smiles? Is it smile? Ah, that actually does it. That creates the smiles of that. I can just copy that. Copy. So that I was able to draw it and then basically get the smiles using the little smile button there. I think also submit. Whoops. That was probably the easiest way to do that. Was just use the editor, hit the smile button, and then copy the text. It entered it into this format, which lets us do other things, which we're probably not going to do. So, what you will be doing on your homework though is creating some smiles. So now you know how to do that. All right. Let's see. Okay, so we created a smiles string for this molecule. Let's try. Ooh, this looks scary. We'll try this compound 12 notch 2/3 inhibitor from homework 3, and we'll try to do it and encode the chirality. Let's see if that works. All right. There's the editor. And I just double checked on a test molecule that this does encode the correct isomeric smiles for the chiral centers. Okay, so let's draw this guy in there. I'll start with the benzene on the left, maybe. And then we have another 7-member ring, it looks like. 1, 2, 3, 4, 5, 6, 7. So just use a 7-member tool. Let's see if that works. Whoa, not that. Can I undo? Yeah, that's the undo. There's a little arrow there. 7-member ring. Okay, so then I'll just kind of fill in some of the atoms. There's nitrogen. This is a amide, and then a nitrogen. Kind of go left to right, I guess. There we go. Benzene, methyl. Uh-oh. There we go. N-methyl. Acetyl bond O. All right, that's looking pretty good for the left side of the molecule. Okay, for the stereochemistry, it doesn't have like dash and wedge tools, but you can just kind of alternate using this little weird wedge tool up here. So there's like the wedge, and if I wanted to make a dash, I just click again, so you can go back and forth, right? Okay, nitrogen. Okay, so then we got. Here's the C double bond O. I'm gonna to keep the stereochemistry. Let's see. Let me see how I can do this. Maybe I'll try to make the. I'm gonna make. I want to keep the C double bond O kind of going upward. So I'm gonna. How can I? Delete this one. Yeah, there we go. Alright, so I hit the X and I deleted one of the methyls. So it doesn't let me do this kind of linear looking acetyl bond O. So the best I can do is just maybe go upward like this. Alright, there's my acetyl bond O. Looking good. Alright, so then we have a zigzag. So there we go. And then downward and then down and O. Alright, there we go. And then this is a tert butyl ester, so that's going to be oxygen. And then carbon, oxygen. Okay, whoops. I can always undo. Okay, now oxygen to make it an ester. Alright, that's looking good. And then what do I got here? I got that wedge thing. I have the two little chains here. Alright, so then this one is going to go downward, and I'll do the stereochemistry last. Carbon, carbon, carbon with 3 fluorines on it. Where's it? X, F, fluor. Uh-oh. Undo. Carbon, carbon, carbon. Alright, so then there's fluorine, fluorine, fluorine. Okay, how do we do the stereochemistry? Hit the little wedge button. Okay, and then for this one, it's the same exact thing. I'll go my smiles keeps changing. Okay. And then it's carbon, 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 carbon. Maybe I have to make it a little larger. How do I do that? Oh, now I'm using my mouse wheel to zoom in and out a little bit. Okay, so fluorine, fluorine, fluorine. Okay, so now, is that looking right? I think it's mostly looking right. Matches, right? And then my last thing is my dash, dash, dash. So I'm gonna hit this once. It's gonna make it a wedge. Then I hit it again, and it makes it dashed. All right, so cool. I think we did it. Did we do it? I think we did it correctly. Tert butyl ester, carbon, carbon, CF3, carbon, carbon, CF3. Okay, good. So how do I make the smiles? Hit my little smile button. Now it's quite a big long little string there. I'm gonna copy this and put it into a Word document just so I don't lose it. Copy. Because I may come back to this one in a bit. Alright, so where's Word? Paste. Alright, there's my smiles. Alright, good. Close. So good. Minimize this. Alright, so that was maybe a more complicated structure with stereochemistry. We created an Isomeric Smiles with the 3 stereo centers. 1, 2, 3. This one was actually kind of more complicated, and it was a little hard to draw in that silly little tool. So in the homework, you will I'm going to ask about this one, and I'm going to give it to you. I'm going to give you the smiles. It's ChemDraw does this very nicely, but that little tool chokes a bit on the structure. So yeah, I'll ask about this one, but in these cases, the COVID-19 protease inhibitor, I'll give you smiles for it. All right. If we're given smiles, is there a way to just identify it if it's a known molecule? And the answer is yes. It's such a very common format that a lot of chemical search utilities will just accept smiles. You just paste smiles in. We can also use PubChem, the database by the National Library of Medicine. Let's try it out. So let's identify this drug molecule from its smile string. All right, so what I'm going to do is copy the text. I'm doing that from the PowerPoint. Control C. Okay, and then we'll go to back to PubChem, and I can actually just paste it right into the search utility. Click. Yeah, so this is Tamiflu, the influenza drug, neuraminidase inhibitor, I think it is. Pretty cool chemical structure, a lot of chirality, and so I can basically look for all the different stuff related to this molecule. It actually also has its own smile strings, and computed properties, all the hydrogen bond count, all those kind of physicochemical parameters we talked about, etc. I think it has. Does it talk about the related compounds? So this is a pretty useful tool to find a lot of information about molecules. And yes, this is oseltamivir. So we're able to identify molecules this way if it's a known molecule. It's used as an influenza drug. All right, good. So also, what else can we do with smiles? Let's start with the easy stuff and then move to the more complicated stuff. We can easily convert smiles into a 2D or 3D chemical structure. That's nice. Let's show some examples of that. Okay. Oh yeah. This is just a brief tangent. Most of you probably have done this before if you've used a computer more than 1 or 2 days in your life. But the idea of saving a screenshot onto a computer, like to save a molecular structure, that's very useful, especially I use that when I'm creating PowerPoint, for example. I can find a really good structure and then incorporate it into my PowerPoint lectures. I am a PC person. I don't really know how to do this on a Mac very well, but Mac people should have some pretty good tricks for this. Also YouTube searches and stuff. But on a PC, you basically hit Shift Print Screen. I would usually then paste the screenshot into a graphics editor. I use this thing called Irvine. It's a free Photoshop type program, and then I can kind of clip out the part that I want, crop the image, make it smaller, do whatever I want to do, and then paste it somewhere. On a Mac, I think it's Shift Command 3, but you can probably Google that, and I just don't have any Macs to test this out. You can also Wikipedia actually has a lot of good chemical structures for common substances like Taxol. Using the screenshot method, I just basically was able to get a high resolution structure of this crazy molecule. You can also save the SVG file. SVG is called vector graphics, and it allows you to. It doesn't have a background encoded. A screenshot has the background, but SVG doesn't, and so then you're able to like set the background to like a funny color or something like that. Okay, good. Okay, so let's do this 2D and 3D chemical structure determination. So we use a tool maintained at UC Irvine. Didn't realize, but their mascot is the anteater, and another vicious animal like our gator. And they have a nice portal of chemical informatics tools that do all sorts of things from one site. Let's see if it's working. There it is. Let's try it out. I'll copy and paste that. Okay, and so I think we can just paste our smiles directly in there. Let's see. So ritonavir is one of the HIV protease inhibitors, and we'll use the Isomeric Smiles from PubChem, and we'll test out this tool. So there's the smiles. Let me copy the smiles real quick. Isomeric Smiles. Okay, it's on my clipboard. So I can delete these sample molecules and paste in this, what is it? It's ritonavir. And let's see if it works. Generate images. Okay, so that allowed me to easily create a two-dimensional structure of a molecule from the smiles. And I think I can copy the image. Let me try pasting that into my Word document. So that's not working, and so this is a case where I could do a screenshot and I could basically get it into my Word document that way, or I may be able to save the image. Save image as. Let me see. On my other window, it's showing. I'm able to save the image. Let me see if it works. I save a PNG file. 1 second. Sorry. Oh, there it is. Yeah. Save. Okay, let's see if that works. So yeah, I opened up that file, and this is a nice image of that structure. I just created using the Irvine tool. All right. So yeah, I'm able to go from a smiles into a two-dimensional structure. All right. Let's see what else do I got. And that's basically the same structure. Yeah. What about a 3D structure? Wouldn't that be cool? Because certainly the three-dimensionality of a molecule is not encoded into smiles, right? You may have the chirality, but a three-dimensional structure is a kind of complicated thing because there's some different I mean, the geometry is complicated, and there might be different conformational isomers, or the shape of the molecule may have a couple of shapes. So this is actually kind of a complicated thing, but we can get a kind of like a tentative three-dimensional structure pretty easily. To thoroughly investigate the three-dimensional structure of a molecule, you might need to use a program called like Spartan. Spartan does that. Maybe Amber, or like a molecular dynamics simulation or something. But we can do a kind of quickie three-dimensional structure. Let's see. All right, so we're going to use something on the Mole Inspiration website to do this. So let's open up. It's called the Galaxy 3D Structure Generator. Let me see if I can open that up. Galaxy 3D Structure Generator. So I googled mole inspiration, top link, and we're going to use the Galaxy 3D structure generator. Okay, so we're going to paste the smiles in to this. Let's see what we're going to use. Vancomycin. So vancomycin is a tremendously complicated molecule, right? It's so I got the Isomeric Smiles encoding stereochemistry. Well, that's the structure, and you can imagine that's not going to be a very tiny little smile string, but the Isomeric Smiles from PubChem is this huge thing, and that this series of letters encodes the entire structure and all the chirality of this. So let's generate a three-dimensional image of vancomycin. Okay, so first I'm going to copy that smile string from my PowerPoint. Copy. Okay, so copied it, paste it, there it is. Okay, pasted it, and I'm going to do generate 3D. So it's processing it. It's going to take a few seconds because it's actually, quite a complicated molecule. Okay, so this is a reasonable three-dimensional image of it, and I can also change the representation. I think CPK tubes. I think I like tubes. Yeah, tubes kind of looks like a normal kind of bond representation, and it does show the different ring systems. This is not necessarily the biologically active conformation, and to really investigate this you need Spartan. But it is cool that we can create a three-dimensional image in seconds that is chemically pretty reasonable, right? Unlike that peptide that we just saw a few minutes ago. Let me see. Maybe I can go find. Do I have that one again? Maybe I'll try that weird peptide that we saw and see if that works also. Okay, so there's vancomycin, and there's vancomycin. That just a random image I created. I think with this I just saved a screenshot of it, so I was able to paste it into my PowerPoint. Okay. So what I'm going to do is I want to go try that crazy cyclic peptide we saw earlier. That I thought the structure was a little ridiculous, and we'll see how this Galaxy 3D tool represents its structure, which I think it'll be a little more realistic. Let's go back a little bit. Where was it? Daptomycin, I think. Yeah, it's here, sorry. Yeah, Daptomycin. Let's go take a look at that, and we'll get the Isomeric Smiles of it. I'll just try PubChem search Daptomycin. There it is, PubChem. It has this probably very, very unrealistic looking two-dimensional structure. Let's go down to the Isomeric Smiles. There it is. Copy it. We'll go to mole inspiration. And let's see here. Galaxy 3D structure generator. Paste. All right, let's see what happens. The cyclic peptides do have some pretty crazy structural features. So this is maybe a little bit better. Let's do the tubes, I think. So you can definitely see this. This looks a little more like a peptide with the kind of alternating amide stereochemistry, and yeah, with the R groups kind of going up and down, and then then we have this other little side chain, and then this series of alkyl atoms. It's like a greasy alkyl chain. Well, anyway, yeah, it's the actual structure would probably require a little bit of computational processing and massaging with something like Spartan. But that, in terms of coming up with a kind of reasonable starting point 3D structure, this is great because it takes like a couple seconds. All right. Okay. All right, so we just finished the generation of 2D and 3D structure section. Next thing is the prediction of drug likeness using computational tools, mostly getting those parameters like C log P, polar surface area, and stuff like that. I think I'm going to just do this in the synchronous lecture, so we'll end this lecture a little short. Oh, and then we'll also get into fun stuff like prediction of metabolism and sites of phase 1 and 2 metabolism using computational tools. All right, so that will be that'll be next time. All right. Why is the okay? Yeah, my recording got a little messed up here. All right, cool. Now you can see the whole page. All right, yeah. So anyway, we'll continue with these things next time.